for giving me such opportunity to present my work here. So, okay, so our work is we actually design quantum refrigerator in the spin chain model that can be uh, uh, implemented or can be shown in the laboratory. So because spin chain can be actually experimented, visualized. Can't you see the slide?
Are you sharing the screen? If it is,
Okay,
then we cannot see your screen.
Oh, okay. Can you see my screen now?
Now it's visible. Yeah.
Yeah. Okay. Sorry. Okay. So these spin chains can be visualized in the laboratory. So that's why we try to build this refrigerator in the quantum spin chain with the effect of environments. So this is the outline of my talk. I'll first talk about what is a refrigerator usually that we have see actually in regular basis, and what is quantum refrigerator. Then I will talk about some open quantum system, how it is actually utilized, how we are utilizing this for refrigeration. And then I will talk about the design of a refrigerator. And then I will talk about the results, and then I conclude my talk. So first, a refrigerator. So suppose there is a system S, which is in thermal equilibrium with the temperature TE. Now, if you want to refrigerate the system S, you have to include some machine or some machine in between system and environment, which is actually take out the heat from the system and then include in the heat is flowing from system, it will take out the heat from the system and deposit in the environment. So we will say that the heat of the system will getting colder. And usually in mathematics or in thermodynamics, we actually take some some direction as positive for this case. So we will take that the when heating flowing out from the system to environment is a positive. And we'll tell this it is a refrigeration when the temperature of the system, suppose TR, that is TR will less than the TE. Now, the usual refrigerator that works is this engine where the system is connected to two bath. One is colder, one is hot, and there is some work has to be done which actually take out the heat from the cold bath and deposit it in the hot bath. And then in between, then this system get colder. And this kind of system was first described by Sadi Carnot first. This is the usual refrigerator. Now, what is quantum refrigerator? So in quantum refrigerator, suppose there are n system here. Suppose there are n subsystems, and each subsystem has some n-level system, each subsystem, and each subsystem is connected to a thermal bath, which is, and they are equilibrium with the thermal bath. So each individual system is given by this Gibbs have state is as the Gibbs form. So HI is the local Hamiltonian of each subsystem, and they are equilibrium. And from this subsystem, we choose one system that is the target system, which has to be cooled. So this is the main framework for quantum refrigerator. And then at time greater than 0, we actually include there is a interaction between the subsystem. And when this interaction is switched on, this evolution of this total system is governed by this equation. And this equation is called quantum master equation. And this Hamiltonian then have two parts. One is local part and one is interaction between these subsystems. And we are actually interested in one part where this d rho is dt equal to 0, which is called the steady state. And we are actually interested in this part, and we'll check if the refrigeration is happening. Suppose refrigeration means the temperature of the system is lower than the initial system. Now, how we'll do that? So when we actually have total system rho S, we actually trace out the other parties, other system, and we check the steady state properties of this individual particular target system. And now, how to define temperature? So for our case, how we define temperature? Suppose this individual local system is given by HI, and then say an auxiliary state, which is have some in arbitrary temperature e to the power minus beta prime HI. And this is a Gibbs state. and we check at in any time how close our system, suppose rho I in this rho I is the steady state temperature, and how close this state to the some rho I, this rho I prime. And we take rho I prime, and then we minimize this rho I distance with respect to beta prime. So when so this beta is steady state, thus means this, suppose there is some rho I, and you take the trace distance between the steady state and the rho prime and minimize this distance, and we check how close the subsystem to an give state. So this means what give state actually close to the to this thermal, to this our steady state system. And for this distance measure, we have taken taken trace distance and relative entropy distance, but here we only focus on this trace distance measure. Now refrigeration means this one, obviously this one. So when this temperature is the steady state temperature lower than the initial one. Now I'll talk open quantum system. So in open quantum system, there is a system HS, which is given by the Hamilton HS, and it is initial state rho is 0, and environment has some Hamilton HE and rho E, and in between them there is an interaction which is governed by this lambda HSE. So at initial time, the state of the system is a product state, which is rho S tensor rho E, and then we evolve the system by this unitary by H total, and to check the system properties, we actually trace out the environment. Now this in tracing out is not so easy task here, because environment has some large degrees of freedom. So in that case, we have to do some approximation, which is called an Born approximation, and another is Markov approximation. So what is Born approximation? That is the at any time there is no correlation is growing between system and environment. So always that any time this will be a product state. And what is Markov approximation is that at t suppose at tnth time, is the state of the system at tnth time depends only on the previous instant of time, and by applying this we actually end up to this equation. And then we do secular approximation, which is, how do we do this? Suppose lambda HAC is given by this form, where this L alpha E alpha is the operating on the system and the environment part, and by secular approximation, we actually, when we integrate this system, we actually throw all the highly oscillatory term, and then we actually end up to this equation, the usual Willenbrand-Master equation form. And this gamma omega depends on the environment part, and this operator L alpha omega is the called Lindblad operator or jump operator. And this E and E prime is the eigenstate of the system Hamiltonian only. So this actually corresponds to a jump between system energy state E and E prime. And this type of equation is called a Redfield-Master equation. So we actually use this equation. Now, for our case, we have taken this environment to a bosonic environment. And for that case, we will get to this Lindblad-Master equation, where this gamma omega, gamma minus omega is basically the correlation function in the environment. And this actually, for bosonic system, this boils down to an bosonic distribution. And this F omega is actually can be taken otherwise, and then we actually get some other non-Markovian or Markovianity in the system, in the system. And for now, this Lindblad operator, which is this form, which is this E and E prime of the eigenstate of the total system, that is HS. So this has two parts, which is local part HI, and another is interaction between them, HIN. So this can be a function of some Hamilton, some scalar HI, and some H interaction can be a function of JIJ. Now, depending on the depending on the strength of this HI and JIJ, we actually can describe two other master equation, which is called local master equation, and another is global master equation. So in local master equation, the individual local system strength is highly greater than the subsystem interaction. So then this local master, this Lindblad or jump operator basically described by the only local part of the system. And this EIL Lindblad operator is formed by local only the HI eigenstate. And this is called local master equation. And usually the global master equation, this HI interaction strength is comparable to this JIJ. So that's why it's called global master equation. And this master equation, why use that? Because these two equation has these two equations are valid, they have individual validity region where they are individually valid. But in some region, local master equation can be failed, then global master equation can be used, and but in there some region, there can be global master equation can also fail, and then local master equation is their option. But we actually check what is the case if we evolve the system by master equation as well as global master equation. Can we get what is the change of refrigeration here? So now we talk about the design of our system. So but before design of the system, we will talk about what is previous work. There first in the 2010 there is some work came, that is by Popescu, the how small this thermal machine can be. So they have take a two-level system. Suppose this E1, E3, and TC is connected to a thermal bath with TC, and this is connected to heat bath TH. And then they have taken some engine qubit, that is they have temperature TR. So at initial time, they have all the product state, which are in row 1 can be an thermal state. And they have taken such E3 operation because they want to take the autonomous quantum absorption quantum refrigerator. So that's why they have taken such all the values as such a way. And then at t greater than 0, they actually introduce this interaction. Why this interaction actually taken? Because if you see, 0 is the ground state and 1 is the eigenstate. And by this, 0 is the ground state and 1 is the excited state. And by this application of this each interaction, they actually change the population of the ground state. So actually getting the population of the ground state is getting higher with the application of this H interaction. So that's why they wanted to check their population, the temperature of the system can be described by the population of the ground state. That means how the ground state population is getting higher and higher. So then we'll say that we will actually refrigerate the system more and more. Now, by introduction of this H interaction, the system would governed by this Lindbergh master equation. And then for taking what is the output, their TC is the target qubit in their case. And they calculated the TC for steady state in any individual time. And this Ri0 is given by this form. This is actually an Boltzmann distribution for Boltzmann. They are following Boltzmann distribution. So at any time, the temperature can be defined from this relation, and they have defined their temperature by this form. Where EI is EI basically the temperature. I mean the strength of the magnetic field basically. And then this is the population in fast and ground state. Then this is the temperature coming that I said that the coming from the population inversion case. And another thing that can also describe the refrigeration, that is the heat current, that is the amount of heat going out from the system to environment. So these can be described by this HS, where this Li is the Lindbergh operator. Now, as we have described, our definition is the minimization over this beta prime, the trace distance between rho I prime and rho I. And we see that we actually analytically show that if we take the trace distance to be this form, then for spin up system, when the system are spin up, that is two-level system, our temperature difference boils down to this Popescu, this inversion temperature by this population inversion scenario. So now I will take our design of a temperature refrigerator. That is, at initial time we have three systems. One, they have both thermal, and they are both equilibrium with the T1, T2, T3. Where the T1, the system T1 that is connected to T1 is our target system that we want to cool. And each individual system is governed by, they have each individual magnetic field, HI, sigma IZ, governed by this Pauli Z matrix. And each initial time, this is the thermal state. And this is the total system, which is decoupled, and the product state. Now at t greater than 0, we actually on the dynamic switched on. And for calculation, for our case, we have to check the spin chain, how the spin chain actually helping for refrigeration. We take defined type of interaction strength between this system. And for our first case is the XY interaction, which is an XY exchange interaction in the XY plane. And there is the interaction in the ZZ plane. And then is the antisymmetric exchange, which is called the Dzyaloshinskii-Moriya or DM interaction. And we have checked what is the good or something I say very useful for refrigeration. And they usually evolve by this master equation. So we ask the question how system parameter play a role in achieving refrigeration. That is the strength of the interaction between the Hamilton subsystem in play a role in achieving refrigeration. And then we try to find how different interaction strength play a role in achieving refrigeration. And then we see what is the presence of disorder has any deteriorating effect in the refrigeration. So I will talk about our results. So when we are using local master equation, that is H is greater than Jij, in that scenario, this will be our master equation. And then we actually check the target system temperature and the heat current. When we see that this red one is a jet interaction, which does not help in refrigeration. So by increasing the amount of refrigeration, amount of jet interaction strength, the refrigeration does not decrease. So it always constant. But when you introduce XX and DM interaction, which is this circular and the square box, we see that the introduction of XX and DM interaction is actually helping in refrigeration. And if we change the interaction strength more and more, the refrigeration is more. And also the heat current is also so positive. So both matches. So amount of heat actually going out from the system to environment. So why this is actually happening? Because if we see XX and DM interaction are this is some kind of exchange interaction, which is actually grow some population in the ground state. So that's why we actually getting higher refrigeration, getting refrigeration by XX and DM interaction strength. Now I'll talk about what is disorder in this case. So first, to calculate to effect on the disorder, we will just discuss the short discussion about disorder. So disorder is, suppose for individual, the strength between this subsystem can be different. So for individual parameter, can be different realization of the system. So in order to do capture the effect of disorder, we have to average over all the system parameter. So that's why we have this averaging is called coincident averaging over all the disorder. So for that case, if G is the parameter whose value are chosen, this is the disorder. We are putting disorder in the G. This value can be here we choose from Gaussian distribution, which is a mean G and standard deviation sigma G. When this sigma G actually quantifies the strength of this disorder. So in our case, this is the system. And we check this interaction strength Jij choosing from this Gaussian disorder, each choosing from Gaussian disorder. So this Jii plus 1 is getting from Gaussian distribution, so we mean G and the standard deviation sigma. So for each individual interactions G and sigma, with this we evolve the total system by this local master equation. And from each individual iteration, we actually get the temperature for the subsystem. And then we actually average over all the temperature. And this is called actually coincident averaging. And for that case, if you see, check the A and B figure, that is we increase the mean value of this XX and DM interaction and check that and putting it disorder, we check what is the refrigeration is the amount of increasing or decreasing. And if we see this disorder is given by this solid circle, and if we see this value of refrigeration is very less. I mean, we're starting from temperature to be 1, it is actually getting very less amount. But one thing is that by including the disorder, this effect of refrigeration does not go away. It's kind of, we say this is robust. So we are actually getting the introduction of the disorder does not deteriorate the refrigeration. This actually this is robust. So we can say that. And from C and D, we actually increase the amount of disorder. That is, we increase the standard deviation by keeping some some particular mean value of G, XX and DM interaction. And it's checked that this by also increasing the amount of disorder, we actually getting refrigeration. So we can say our refrigeration is actually robust with the disorder. Now I will take. If you do the global master equation, so that is all the interaction strength is comparable to the Jij. In this scenario, we have get this kind of refrigeration where T1 this is the average that we have also taken the disorder in the global master equation. if we see that in this scenario, the anti-ferromanagnetic strength between this, ferromanagnetic strength between this subsystem actually helping in refrigeration. And this strength, the refrigeration actually getting higher with respect to the, if we increase the interaction strength. And one thing that is something comparable that is not there in the local master equation, that is in the global master equation, when we calculate this refrigeration in the by terms of heat current, we see this is a negative. So it is actually saying that the something something physically not correct, but usually people have shown that the local and global master equation can be used such a way there is no comparison between them. So in that case, the refrigeration does not, also people also showed that the refrigeration does not mean the heat current should be positive or negative. So in that scenario, we actually get this kind of case when we using global master equation. And now I will take the refrigeration with higher dimensional spin model. That is, suppose there are two spin, which is at temperature T1 and one is temperature T2. And each individual system is the SRJ, on the jet component of spin value. And each individual qubit is in individual system is given by this Gibbs form. And each system is now N level or D level system, J level system. And when T greater than 0, when the interaction is switched on, we have taken two types of interaction. One is XYZ model in higher dimension. And also there is another model which is not actually available for spin-up system. This is called bilinear biquadratic Hamiltonian. So this is start from spin 1 to spin greater than half. And which asks the question, does the increment of dimension play any role in refrigeration? And for that scenario, we have taken, suppose the initial state, the target system is a spin-up system, and the other system is a spin-in system. And now you increase the dimension of the spin-in. Suppose this is a spin J, in dimension by J, and take the temperature of this this T1. And for that case, we actually use the local master equation. We have chosen such interaction strength. And I see that by increasing the dimension of this other party, actually the refrigeration is much more, and also the heat current getting positive and getting more and more. So this is the scenario for when our system is spin up, another is spin J. Now, if we change the spin up to spin J system, so both the system are now spin J and spin J. In that scenario, we actually getting the same figure. This temperature to be getting much lower and lower with the time by increasing the dimension, and also the heat can getting more higher. And for this case, because spin up system, we can actually do the population inversion, and for spin D system, we actually this this minimization over the trace distance measure. So that's why we want to check what is the individual qubit entropy getting how this individual system entropy is getting lower or not. So we see that when the refrigeration is happening, the individual system is the target system basically getting the entropy of the target system getting lower and lower. So we can say both the things are matches here. So, and we are getting refrigeration with higher dimension. So this is the kind of take home message that with increasing dimension J, one can build better refrigerator. Now for that, now we want to check what is the scenario BBH model other than XYZ model. So in that scenario, we actually also get the same type of result that now here we increase the interaction strength between the individual subsystem, and I check that the increasing the individual strength subsystem, we are getting lower and lower with increment of the dimension. And we say that the dimensional increments actually helps refrigeration, and the refrigeration also possible in different type of interaction in present. Now I will conclude that is our design of refrigerator using spin chain that can be also implementable in laboratory, and refrigeration is robust against disorder. And now if the interaction strength is comparable to the local magnetic field, we showed that the refrigeration is achieved by using global master equation that is more incomparable to the local master equation. And increase the dimension of the local subsystem is beneficial for achieve refrigeration. Okay, so this is the collaborator that I have worked till now, and thank you.
So thank you, Tanoy, for this beautiful talk. So our session is now open for question. So participant can ask question or write this question on the chat box.
Thank you for your talk. I would like to understand how you are bringing down the temperature of your system. So could you please explain by which operations you are bringing down the temperature?
Okay, so suppose we are actually using this this is the definition of our temperature. So beta ist is the steady state inverse temperature. We are suppose this individual initially
This
they have
is,
some temperature.
Beta is Boltzmann constant, right?
No, no. The beta is the inverse temperature.
Okay.
This Boltzmann constant is 1 here.
Your voice is breaking.
The beta is the hello. Can you
Yes,
hear me?
Yes, now it's okay.
Okay. So beta is the inverse temperature of the target system. So we take, suppose this is the steady state, this is temperature, this is the state rho I st. Now we take some individual arbitrary give state given by this rho I prime, and I check what is the minimum, which give state actually closer to this rho I st. So that is our temperature of this individual subsystem. Hello?
Yes. But how, if, for example, if I have 10-degree, you see, temperature of my subsystem, and you would like to bring to the 2-degree Celsius, then how you are doing that? Okay, you are just comparing with 2-degree.
With the initial temperature to some final temperature at steady state, that can be, it is lowered or not. It can be, suppose if we instructions choose such a way, it can also be heated, but we choose such an parameter regime that is actually getting lowered or not. There can be some particular parameter regime which can be, there is no refrigeration at all, but we choose such a way that it is a refrigeration happening. It is not some particularly you can choose this state scenario.
Yes, but there should be some operations which will bring down the temperature.
Because there is some prediction by this paper. Actually they have taken this is kind of exchange interaction, which is why they have chosen so, because suppose this 0 1 0 is the state of the system, and 1 is the excited state, and 0 is the ground state. Now application of this H interaction, they actually change the population of the system, because this excited the population of this ground state will be get higher. So in that scenario, the refrigeration means how much the ground state is actually populated. So if we increase the population of this ground state, we will say that this system is more refrigerated. So this is the case for spin-up system, because they are two level, and you can say that how the ground state population getting higher or not.
Okay, thank you.
Okay.
So are there any other questions?
Generally, when the temperature goes up, there is, in my understanding, when you have lattice, then there is a vibration of that lattice, and this is due to phonons. So
yes.
In your case, you are using some states and bringing down those states. Then it means that you are bringing from higher energy to the lower energy.
Some some kind of, you can say that that can also that I don't know, that can be straightforward or not, because some with respect to energy, there can be some definition of temperature also there, by keeping this energy fixed or energy to be lowered. So that we have not checked that the initial system has higher energy than the lower than the final system. That can also be checked, that if we check the energy of the system.
Thank you.
Okay.
Any other question from other participants? If it is not, then we are ending our session here. And thanks again to our speaker. And we are hoping you to help you in next year. And so, yeah, and all participants are requested to present tomorrow's session. Our session will start from 10 a.m. So see you tomorrow.
Thank you.